Most people step right over it, mistaking it for old road gravel or weathered construction debris. But that gray-green, crumbly rock underfoot might not be just another volcanic relic. It could be kimberlite, the deeply sourced igneous rock that serves as Earth's primary conveyor belt for diamonds. The irony? Its appearance is so unimpressive, muddy, vesicular, and often oxidized, that even seasoned rockhounds have tossed it aside, unaware of the billion-year-old pressure story it holds. Kimberlite is a volcanic breccia that forms deep within the mantle and erupts explosively, bringing diamonds and indicator minerals to the surface. Its texture varies widely, often confusing amateurs. Some samples look like potstone or soapstone, while others show scattered olivine phenocrysts in a clay-altered matrix. These are not the glittering, glassy crystals most people associate with gemstones. But therein lies the opportunity, because this visual homeliness acts as a natural camouflage, hiding riches in plain sight. You can start to separate kimberlite from lookalikes by checking for subtle traits. Does the surface crumble with finger pressure, especially when wet? Are there rounded fragments of different rock types embedded within it? Like a mineral fruitcake? Is the rock surprisingly light for its size, hinting at gas-charged eruption history? These signs matter, especially when spotted along dikes, fault lines, or weathered depressions. But the real signal isn't the kimberlite itself, it's where it appears. Diamondiferous kimberlite pipes are rare and typically small in surface area, often under a hectare, but they punch deep, sometimes over 150 kilometers into the mantle. They erode easily, spilling out their load of indicator minerals. If you find the right kind of ugly rock within stream concentrate, it's a downstream whisper that something richer may lie upslope. Ironically, the best clues to kimberlite are often not the rock, but its mineral companions. Deep origin garnets, black metallic grains, or oddly shaped green olivine crystals. But you have to notice that first rock to start the chase. And once you do, the next question becomes, what exactly should you look for to tell it's not just basalt or serpentine? At a glance, most people can't tell the difference between a piece of weathered basalt and a fragment of kimberlite. But the distinction, once learned, can change everything. True kimberlite and lamproite, both deep-sourced volcanic rocks capable of carrying diamonds, have diagnostic textures and inclusions that are subtle in isolation but unmistakable in context. Learning to see them is the foundation of any serious diamond prospecting effort. Kimberlite, when fresh, has a greenish-blue or bluish-gray hue due to its high olivine content. In the field, though, you're rarely looking at fresh rock. Most exposed material has been heavily altered by weather and groundwater. This creates a clay-rich, earthy surface with a dull luster and a chalky feel. Look for embedded, rounded nodules of peridotite material or fragments of other rock types. Xenoliths, entrained in the matrix. These inclusions hint at violent emplacement from deep below the crust. Lamproite, a less common but still diamond-hosting rock, often weathers to a buff, tan, or yellow-brown tone. It contains rich concentrations of phlogopite mica and can present a greasy or slightly soapy texture when wet. In both rock types, the presence of small green to black crystals, especially garnets, spinels, or ilmenite, is not accidental. These are the signature indicator minerals. Most field prospectors begin training their eye by breaking open suspect rocks. Kimberlite will sometimes yield olivine grains that appear glassy or pale green, but crumble easily. You might also spot tiny metallic-looking flecks, possible ilmenite or chromite. These minerals don't just co-occur. They're physically carried up by the same eruptions that bring diamonds to the surface. Their presence doesn't guarantee diamond content, but it raises the probability significantly. An overlooked tip: use a hand lens to examine mineral grain shapes. Rounded garnets or pitted chromite crystals suggest secondary transport, likely downstream from the source. Angular grains, or matrix-bound indicators, imply proximity to the pipe. And don't forget the importance of magnet response. Ilmenite is weakly magnetic, but consistent across real kimberlite clusters. Running a simple rare earth magnet over crushed samples can flag its presence quickly. You can carry all the right tools and know every indicator mineral by sight. But if you're not in the right terrain, it won't matter. Diamond pipes don't erupt randomly. They follow specific geologic rules tied to Earth's deepest and most stable structures. And the most revealing clue? Most of them are hiding in plain sight along cratonic margins, ancient continental roots, where the lithosphere is thick enough to support diamond stability during ascent. Cratons, such as the Kopval in South Africa or the Canadian Shield, are relics of Earth's early crust, stable for billions of years. Kimberlite and lamproite pipes erupt through these regions along pre-existing weaknesses, fault zones, fractures, and ancient rift systems. That's why diamond-bearing pipes often cluster near the intersection of old fault lines, or lie hidden beneath shallow alluvium in otherwise flat terrain. But these pipes rarely form hills. Instead, erosion cuts them down faster than surrounding rock. Over millions of years, they weather into shallow depressions, natural collection points for surface water and sediment. In the field, a circular or elliptical wetland surrounded by slightly raised terrain might not just be a seasonal pond. It could be the eroded top of a kimberlite pipe. Savvy field hunters also know to scan for meanders and back eddies in river systems that drain from potential pipe zones. Diamonds and their indicator minerals are heavy, much heavier than quartz or feldspar, and tend to concentrate on the inside bends of rivers behind large obstructions or in ancient paleochannels now dry or buried. Old river beds that have shifted course over centuries often carry the best secondary deposits, especially when the source pipe has eroded entirely. Geological survey maps, often available from national or state mining bureaus, reveal even more. Look for ultramafic intrusions, diatremes, or volcaniclastic breccia on regional maps. Coded signals for potential kimberlite or lamproite. Some maps also show airborne magnetic anomalies, which can betray the circular magnetic signature of a buried pipe. The circularity is key. Unlike linear dikes, pipes create concentrated, round targets. Still, all this structure and theory means nothing without visual proof. When these terrains shed their secrets, they do so in tiny fragments washed downslope. The next step is knowing what to look for in that runoff. Specifically, which heavy minerals signal you're on the right track. Most people pan for gold, but those chasing diamonds are after a far quieter signal. A gritty mix of heavy, dark, and often unimpressive grains that don't sparkle, but speak volumes. These are indicator minerals, and when they appear together in the right proportions, they serve as the geologic breadcrumbs leading back to a diamondiferous pipe. In a sluice or pan concentrate, the appearance of pyrope garnet, chromite, ilmenite, and chrome diopside, especially in tandem, is a major red flag in the best way. These minerals are all denser than quartz and feldspar, so they settle low and tend to accumulate in traps just like gold does. But unlike gold, they're often matte or subtly colored. Pyrope shows as deep red to purplish grains, ilmenite as black metallic slivers with a weak magnetic tug, and chrome diopside as bottle green transparent fragments. The visual signals are subtle, under natural light. Pyrope garnets can look like dark grains of sand until you catch them with a loupe or LED beam. That's when their true color, often a wine red or magenta, emerges. Chrome diopside, when wet, can show a vivid emerald hue, but may fracture easily when tested. Ilmenite appears as flat, shiny black flakes that respond slightly to a magnet, unlike chromite, which is denser and often more lustrous. Concentration patterns matter just as much as mineral ID. Finding a single garnet in a pan means little, but clusters of 3 or more, especially accompanied by black grains with weak magnetism, suggest a sweet. The sweet concept is essential. No single mineral guarantees proximity to diamonds, but the correct combination increases probability exponentially. This is why professionals often use number 20 to number 40 mesh sieves, 0.85 mm to 0.425 mm, to isolate the heavy fraction consistently. Another clue lies in abrasion. Rounded grains suggest long-distance transport. Angular, fresh-looking grains mean you're closer to the source. If these indicators appear within a few kilometers of a known ultramafic structure, the likelihood of a diamond-bearing pipe increases sharply. In well-mapped terrains, finding indicators upstream of a known barren pipe might even suggest an undiscovered secondary pipe nearby. Still, these clues aren't definitive. Just as gold can appear in isolated pocket deposits, indicator minerals can be misleading without context. That's why most seasoned field prospectors treat a pan full of garnet and ilmenite not as a discovery, but as an invitation to escalate testing. And that's where the first serious pass begins. A quick, mobile method that can confirm whether the area deserves deeper attention. The difference between wasting a day and identifying a high potential zone comes down to your first sweep. This is the lightweight reconnaissance phase. A minimalist toolkit, mobile testing, and a tight focus on indicator density. The goal isn't to prove a diamond source, but to eliminate false leads quickly while flagging real contenders for deeper study. Start with a simple rare earth magnet mounted on a telescoping stick or handheld wand. Sweep the surface of shallow streams, tailings, or weathered depressions. Ilmenite and magnetite, common kimberlite indicators, will tug gently. Unlike junk iron or hematite, they often appear as thin flakes or compact black grains with a slight metallic sheen. Don't mistake them for industrial slag. Location matters. If you're miles from any roadbed or mine, the odds tip toward natural origin. Next, deploy a sieve stack. Number 20, 0.85 millimeters. Over number 40, 0.425 millimeters, is standard. Pour fine stream sediment or soil from the eroded depression into the stack, shake with water, and focus on the middle fraction. Discard anything above number 20, too coarse, and watch carefully for color flashes and grain luster in the number 40 concentrate. What you're looking for now is sweet behavior. Pyrope garnets appear as translucent reddish or purplish grains. Chrome diopside emerges as glassy green. Black grains that stick weakly to your magnet may be ilmenite or chromite. If they're also dense, rounded, and not shiny like slag, they're suspect. Note everything and begin counting. 3 garnets per pan means almost nothing, but 10 per pan, or consistent appearance across grid samples, starts to indicate a pattern worth tracking. This is also where weight in hand comes into play. Pick up any larger rock fragments in the area that appear out of place. Does it feel oddly light or heavy for its size? Kimberlite often feels lighter than it looks, crumbly, porous, clay-altered. In contrast, ilmenite and chromite nodules will feel disproportionately heavy and may carry a smooth, matte finish. If the rock responds to a magnet and seems out of geological place, it may be a deep origin fragment shed from a nearby pipe. The sweep phase is about rapid elimination. Areas without indicator density, magnetic response, or sweet diversity can usually be dropped. Those with concentrated indicators and heavier than normal sediments, especially near erosional depressions or paleochannels, graduate to grid testing. Under long-wave UV light, some rocks light up in ghostly hues, blue, green, yellow, even white. For beginners in the field, this can seem like the ultimate shortcut. Shine a light, and if it glows, it's a diamond. But in truth, UV fluorescence is both a powerful screening tool and a notorious source of false hope. Knowing what to expect and what not to trust is critical. Many natural diamonds fluoresce blue under long-wave UV, and strong fluorescence can indicate a high nitrogen content in the crystal lattice. But not all diamonds fluoresce, and crucially, many non-diamond minerals do. Calcite, fluorite, scapolite, and even some feldspars can produce intense UV reactions, sometimes mimicking the icy blue or soft green expected from diamonds. That's why relying on fluorescence alone, especially in field conditions, is a fast track to disappointment. Here's what matters more: pattern, consistency, and intensity under both long-wave and short-wave UV. Real diamonds that fluoresce usually do so uniformly, with a clean, even glow across the surface. Simulants or imposters often show mottled or spotty fluorescence, or none at all. If you found a transparent or pale stone that fluoresces strongly blue and matches high specific gravity, 3.52, it's worth escalating to further tests. But UV is even more useful earlier in the workflow, as a screen for certain indicator minerals. Some garnets, especially norangite-rich pyropes linked to kimberlite pipes, may fluoresce faint orange or dull red. Ilmenite usually doesn't fluoresce, but accompanying calcite or serpentine in the matrix might, helping highlight brecciated rock pieces in poor light. A quick UV scan over concentrate trays at dusk or in a shaded field tent can reveal overlooked targets for closer inspection. Fluorescence also plays a role in separating fakes from genuine finds later in the chain. Synthetic moissanite, a common diamond simulant, rarely fluoresces in the same way. High-index glass or cubic zirconia often shows green or yellowish fluorescence, visible red flags. Even some corundum, sapphire/ruby, glows, but at a higher intensity and with a different luster profile. Few tests offer as much satisfaction in the field as watching a diamond tester needle spike to the top. But relying on that spike alone is risky. Thermal conductivity testers, standard in gemology kits, are easy to use but equally easy to misread when the target is embedded, dirty, or not actually a diamond. Worse, some of the most convincing fakes, like synthetic moissanite, can trigger the same result. That's why understanding how and when to use these devices is essential for reliable field work. Diamonds conduct heat extremely well, far better than quartz, glass, or corundum. A handheld tester applies a tiny amount of heat to the surface and measures how quickly it dissipates. On a clean, polished diamond, the result is nearly instant. But in the field, most candidates are rough stones, sometimes coated in clay or oxidation. This interferes with contact, often producing false negatives. Before testing, clean the surface with water and gently abrade one facet with a soft file or diamond pad, just enough to create a contact window. Moissanite, however, presents the bigger trap. It also conducts heat efficiently, almost as well as diamond, and in older testers, it will give the same diamond reading. That's why many updated testers now include an electrical conductivity probe. Diamond is an electrical insulator. Moissanite conducts electricity. So when you get a thermal spike, follow up with a probe that tests for current. If it conducts, it's likely moissanite. If it doesn't, and the thermal reading was high, the odds of a true diamond increase. To run both tests properly, you need a stable surface, dry conditions, and ideally a stone that's freestanding. Embedded crystals in matrix, or stones trapped in iron-rich crusts, often give inconsistent results. It's worth removing suspect stones from their matrix or sediment layer and drying them fully before testing. Another quick field tactic: test known samples first to calibrate your expectations. Bring a piece of quartz and a confirmed piece of moissanite or glass. Compare thermal and electrical readings on these before testing unknowns. It helps train your touch and identifies instrument drift, especially under variable temperature conditions. Even with these tools, you're still in a gray zone until other properties confirm the identity. A diamond tester is fast, but it can't distinguish between a high-value rough and a worthless simulant unless the rest of the mineral context aligns. That's why smart prospectors treat it as just one data point in a chain, and move next to unmask the most common false positives in indicator suites: zircon, garnet, and corundum. It's a moment that misleads countless well-meaning prospectors. A pan flashes with brilliant reddish grains, dense and glassy, sitting stubbornly at the bottom with the heavies. They resemble pyrope garnet, one of the key kimberlite indicators. But what's actually in the pan is zircon, abundant, often beautiful, and nearly useless for diamond targeting unless properly understood. Zircon is a high-density mineral, often reddish-brown, orange, or even colorless, with a vitreous luster and a blocky crystal habit. It settles in the same pan layer as gold, chromite, and garnet due to its specific gravity, around 4.6 to 4.7, heavier than most indicator minerals. But it doesn't come from the mantle. Instead, zircon is primarily of crustal origin, common in granitic terrains and river systems that cut through metamorphic zones. This makes it a frequent contaminant in heavy mineral surveys. The field key lies in shape and luster. Under a loupe, zircon crystals are often short prismatic or bipyramidal, more angular than the rounded, dodecahedral habit of pyrope garnets. They also tend to show distinct internal zoning under magnification, sometimes with a visible core or color gradient. In contrast, pyrope grains usually exhibit a more uniform color and smoother, more worn surfaces in secondary deposits. Another giveaway is response to UV and light. Zircon may fluoresce weakly but unpredictably, often yellowish or white. Garnets rarely fluoresce. More telling is the double refraction test. If you have a small, polished grain, place it over a printed dot and view it with a loupe. Zircon can exhibit weak double refraction, slightly duplicating the dot. Garnet does not. Hardness testing helps too. Zircon falls between 7.5 and 8 on Mohs scale, slightly harder than quartz but softer than corundum. A small scratch test against a ceramic tile or known reference piece can narrow the identity. Be cautious not to damage your sample unnecessarily, but in field conditions, quick hardness differentiation is often justified when the grain count increases. Zircon becomes a problem in bulk analysis. In some terrains, it vastly outnumbers true indicators. A pan that looks promising because of its density and color can turn out to be a zircon-dominant false positive. That's why documenting ratios in your notes matters. If 80% of red grains are blocky zircon, you're likely outside a kimberlite field. If you start seeing garnet, ilmenite, and chrome diopside in a more balanced mix, especially with angular edges, you might be inside the erosion halo of a pipe. The lesson here is sharp but clear. The more beautiful the pan sometimes looks, the more skeptical you should become. Zircon is common. Diamond is rare. But when the ratios tip and the indicators align, it's time to shift from panning to mapping. Because if those signals repeat over space, not just a lucky scoop, you're entering real prospecting territory. Finding a pan with 3 or 4 indicator grains is a thrill, but it means little unless you can reproduce it. In diamond exploration, repeatability over space is what separates anomaly from source. That's where grid sampling becomes essential. This isn't casual scouting, it's structured reconnaissance, and when done right, it allows you to zero in on erosion halos and prioritize which ground to map, test, and eventually stake. The principle is simple. Establish a defined area, often 100 by 100 meters, and collect samples at regular intervals, usually every 10 to 20 meters. If terrain is rough, you can adapt spacing, but uniformity is key. Each sample point gets a unique label and GPS coordinates. From each site, collect roughly 10 to 15 kilograms of sediment or soil, targeting the B horizon if on land or active trap zones if in a stream. Sieving on-site to less than 2 millimeters saves weight and focuses analysis. Back in camp or at a nearby processing point, Use the same hashtag 20/#40 mesh stack and pan method to concentrate heavies. Log every indicator mineral, not just garnets or chromite, but the full suite: diopside, ilmenite, spinel. More importantly, note ratios and shapes. Are the grains rounded or angular? Are they fresh or weathered? Do multiple points show similar mixes? Patterns emerge quickly. A cluster of 4 to 5 grid points with high counts of angular garnet and ilmenite suggests proximity to a source pipe. A lone high-count sample with surrounding blanks points to secondary transport or reworking. When stream sampling, work both up and downstream. If indicator density increases upstream, you're getting closer. If it drops sharply above a certain point, you've likely passed the dispersal apex. Professionals often plot their sample points in GIS software or even on physical topo maps. Converging high-count samples within a confined area suggest a viable anomaly. If that area also features circular terrain depressions, magnetic anomalies, or rock fragments with weak magnetism and odd mineral mixes, the case strengthens further. Repeatability is also about time. If you return to the same point in different seasons or after rain and get similar indicator concentrations, it confirms stability. Single-sample anomalies can be flukes. Reproducible anomalies signal a real target. The more samples you can confirm, the more compelling your case becomes, for investors, for partners, or for advancing to trenching and assay. The grid was solid. Multiple pan sites lit up with ideal indicator mixes. Pyrope garnet, ilmenite, chromite, even a few grains of chrome diopside. All angular, all fresh. The terrain matched too. Circular depressions in a craton margin, with a known ultramafic intrusion just a few kilometers away. But after weeks of sampling and even a few shallow trench tests, no diamonds turned up. Not even microdiamonds under microscopy. How could such a textbook setup fail? This scenario isn't rare. In fact, it's a rite of passage in exploration. The answer usually lies in one of 3 places: mantle conditions, secondary overprint, or pipe fertility. Let's start with the last. Not all kimberlite pipes contain diamonds. Even with a perfect indicator suite, a pipe can be barren. That's because the presence of diamond-compatible minerals only confirms a mantle origin. Whether diamonds were entrained during eruption depends on pressure, temperature, and mantle chemistry. If the kimberlite sampled a region of the mantle below the graphite stability field, or one that had already been depleted of carbon, it might produce all the right indicators, but no diamonds. This is a fertility issue. Some regions, especially in Africa, Canada, and Australia, have high-fertility pipes with abundant diamonds. Others nearby are mineral-rich but diamond-poor, despite identical surface signals. Another possibility is that the diamonds were there, but were destroyed. Kimberlite eruptions are among the most violent geologic events. If magma rose too hot or too quickly, it could oxidize or dissolve the diamonds en route. In some pipes, only microdiamonds survive. In others, large crystals show resorption features, suggesting partial destruction. In extreme cases, even those don't remain. Then there's secondary overprint. Over millions of years, a fertile pipe can be weathered, covered, or chemically altered. Groundwater rich in carbonate or sulfate can leach diamonds from near-surface zones. Nearby intrusions or metamorphic events can obliterate original textures, leaving only the mineral ghosts of a once-rich pipe. In these cases, the indicators persist, but the diamonds are long gone, or buried beyond cost-effective reach. Understanding this twist reshapes how you view the data. It also teaches the value of microdiamond testing. Even a few grains recovered from a large sediment sample, 500 kg or more, can confirm fertility. Labs use caustic fusion to dissolve host rock and isolate diamonds down to 0.1 millimeters. It's not a cheap process, but it's often the only way to definitively answer the fertility question. What this reversal underscores is the need to validate your indicators, not just by their presence, but by their context. And that means going back to the rock itself. If you can find exposed kimberlite and test its traits directly, you can separate real pipes from misleading trails. It rarely impresses on first sight. Weathered and oxidized, true kimberlite in the field often resembles decomposed shale or clay-altered volcanic rock. But beneath that unimpressive surface lies a distinctive set of traits, chemical, physical, and magnetic, that field experts use to distinguish kimberlite from its many imposters. Recognizing these traits can validate an entire grid or rule out weeks of effort. Start with texture. Kimberlite is an ultramafic volcanic breccia, meaning it's composed of fine-grained matrix hosting angular fragments, called xenoliths, and individual mineral grains, called xenocrysts. This gives it a chaotic appearance. You may find embedded chunks of peridotite, deep mantle rock, rounded olivine crystals, or even pieces of crustal granite engulfed by the eruption. If you break the rock open, expect a friable, sometimes talc-like texture, especially in weathered surface samples. The crumbly nature is a giveaway. Fresh kimberlite may resist a pick, but oxidized material disaggregates easily in hand, often leaving greenish powder on your fingers. The matrix may be dark gray, pale green, or even bluish when fresh, blue ground, turning to yellowish brown or tan, yellow ground, as it weathers. The weathered form is more common at the surface and more prone to misidentification. Magnetic response is a key test. True kimberlite often contains magnetite, ilmenite, and sometimes spinel, giving it weak to moderate magnetic attraction. Run a rare earth magnet over broken samples. Don't expect a strong pull, but a slight stick or consistent grain reaction is a reliable sign. If the rock is completely non-magnetic and lacks visible heavy minerals, it's likely not kimberlite. Look also for indicator flashes. Tiny grains embedded in the matrix, visible with a loupe or microscope. Pyrope garnet, for instance, may show as rounded pinkish inclusions. Ilmenite appears as metallic black flakes, sometimes weathered to a rusty halo. In high-indicator rocks, you might also see serpentinized olivine, altered into fibrous or waxy green material that adds a greasy feel to the surface. Field acid tests can help too. Drip dilute hydrochloric acid on suspect fragments. While kimberlite itself usually doesn't fizz, carbonate veins, common in altered pipes, will. This can confirm brecciation and fluid overprint, especially near the pipe throat. One often overlooked clue: vegetation. Kimberlite weathers to magnesium and potassium-rich clay, which can alter soil chemistry. In some terrains, pipe zones support different vegetation, either more vigorous growth due to mineral nutrients or patchy clearing due to chemical imbalances. If a ring of unusual flora surrounds a subtle depression, and the rock underneath fits the profile, you may be on the pipe's surface expression. A flawless kimberlite sample means little in the wrong geological setting. That's the core reality of diamond exploration. Context determines significance. The indicator suite, the brecciated matrix, even the faint magnetic pull. None of it matters unless you're within a geologic region where mantle conditions once allowed diamonds to form and survive transport. In short, not every kimberlite is diamondiferous, and not every terrain even hosts real kimberlite. Globally, the most reliable diamond sources align with ancient cratons, continental roots stable for over 2.5 billion years. These include the Kopval, South Africa, the Siberian, Russia, the Slave and Superior Cratons, Canada, and the São Francisco, Brazil. These regions host the majority of known economic diamond pipes and are actively explored even today. In these settings, a suite of pyrope garnet, ilmenite, and chromite in soil or pan concentrate is meaningful. It could directly point to a viable source. But outside these zones, indicator minerals can become geological noise. For example, high-pressure garnets also appear in metamorphic terrains unrelated to kimberlite, such as in parts of the Alps or the Himalayas. Ilmenite is common in many basalt flows. Chrome diopside shows up in ultramafic complexes far from any diamond-bearing pipe. In these cases, field samples may look promising but lead nowhere. It's not just about the rocks, it's about the tectonic story behind them. In Australia, for example, the North Kimberley region and parts of the Northern Territory are legitimate targets. But most of the East Coast, despite hosting ultramafic rocks, is geologically too young and hot to preserve diamonds. In the US, the best-known targets include the Colorado-Wyoming border, parts of Montana, and the Arkansas diamond field near Murfreesboro, locations linked to deep-rooted craton fragments. Most of the western US, rich in volcanic rock, hosts no diamonds at all. That's why pre-survey desktop work is essential. Access National Geological Survey maps, magnetics, and diamond potential layers when available. Many countries now release airborne geophysical data. These can reveal circular magnetic anomalies or kimberlite indicator dispersion patterns. If your sample zone lies well outside these features, reconsider investment of time and effort. Even in high-potential regions, pipe frequency varies. Canada has over 300 kimberlite pipes identified in the Slave Craton, but only about a dozen are economically viable. South Africa's Kimberley cluster includes dozens of barren or near-barren pipes. The lesson? Even in the right region, luck and rigor must align. Even the most textbook-perfect indicator suite is meaningless if you can't legally or safely access the land. Diamond-bearing pipes are often found in deceptively tranquil areas, flatlands, seasonal wetlands, or lightly forested ridges. But each of these landscapes carries unique physical hazards and access complications, especially when exploration transitions from curiosity to active sampling. This is where many amateur efforts go astray, not due to bad geology, but poor preparation. Let's start with the terrain itself. Kimberlite pipes typically erode into shallow depressions or marshy zones. These wet holes are attractive for sampling, but can be deceptively dangerous. Seasonal rains transform them into flood-prone basins. The loose, altered rock around many pipes holds water poorly, turning firm-looking ground into ankle-deep slurry. Sudden sinkage is common, especially when walking on dried mud crusts near stream margins. Always probe with a stick, wear waterproof boots with ankle support, and avoid solo work in these zones. Flash flooding is another underestimated threat. In many diamond terrains, such as Central Africa, parts of Brazil, or the southern US, rains upstream can surge downstream in hours. A dry gulch or peaceful meander can become a torrent with no warning. Monitor local weather and know upstream geography. If the area shows signs of recent silt layering, debris jammed into shrubs, or waterlines above current flow, it's a signal. Flooding is active here. Then comes slope instability. In regions like the Canadian Shield or Siberian platforms, pipe expressions often occur on the flanks of weathered hills or ridges. The soil here, underlain by crumbly brecciated kimberlite, can slide with little provocation. Never dig directly into slopes. Trenching in such material without proper shoring is both illegal and lethal. Soil collapse is a primary cause of small-scale mining fatalities in developing zones, and a serious risk even during light prospecting. Now to legality. In most jurisdictions, land rights and mineral rights are not the same. Public land may still require permits for sampling beyond casual surface collection. Private land may have surface owners who do not control subsurface rights, especially in areas with historic mineral leases. Before conducting any trenching, pitting, or bulk sampling, verify land title through government cadastral systems. In the US, for example, the Bureau of Land Management (BLM) controls much of the Western Territory, But staking claims still require strict documentation and ongoing maintenance fees. In Africa and South America, artisanal mining zones may appear open, but are often governed by local cooperatives, tribal authorities, or national companies. Working without permission not only risks confiscation of samples, but can escalate to legal penalties or conflict. Never rely on verbal permission unless backed by a written agreement or formal license. Even accessing old pipes, abandoned or undeveloped, requires caution. Some are protected for environmental reasons. Others are held dormant by companies waiting for favorable market shifts. Trespassing on these properties, even unknowingly, can void any claim you might try to make later. When your indicators show promise and terrain checks out, the next decision isn't about where to look. It's how to separate the heavies efficiently. The wrong method wastes time or loses finds. The right one not only accelerates discovery, but preserves subtle clues like garnet zoning or grain angularity. Whether you're in a remote riverbed, a trench grid, or working concentrate from a shallow depression, choosing between pan, sluice, and jig depends on material volume, water access, and target particle size. The pan remains the prospector's workhorse, for good reason. It's portable, requires no setup, and works with minimal water. For scouting or follow-up grid samples, especially with less than 20 kilograms of material, nothing beats a controlled pan session. But panning is slow and subjective. It depends heavily on operator skill and consistency. What one person isolates as a clean concentrate, another might discard. It's excellent for seeing the mix of indicators, garnet, ilmenite, chromite, within a sample, but not ideal for bulk processing or quantifying frequency. The sluice steps in when stream flow is available and sample size climbs. A simple sluice box, ideally 60 to 90 centimeters long, fitted with miner's moss and a few riffle bars, can process up to 1 ton of material per day in good hands. Water flow should be moderate and even. Too strong, and you lose fines. Too weak, and heavies never settle. Pre-screening to 5 millimeters or less improves efficiency. Feed the sluice slowly, and test tailings periodically to ensure indicator minerals aren't washing out. Sluices shine when processing material from eroded pipe rims or alluvial channels where heavy minerals are dispersed in bulk. The jig, however, is the most precise, if the most demanding. Mechanical jigs use pulsating water to stratify particles by specific gravity. In diamond recovery, they're favored in both field pilot plants and commercial operations. Portable jigs exist, though they require more water and power. When correctly tuned, a jig can separate diamonds and indicator minerals from quartz, feldspar, and light gangue with minimal loss. They're especially useful in coarse gravel, or when a high volume of plus 0.5 millimeters material is present. But without flow control, jigs can misfire. Too much turbulence, and lights mix with heavies. For field trials, the sweet spot often lies in combining methods. Use a sluice for initial bulk separation, then pan the concentrate for mineral ID. If results look promising, especially repeated garnet/ilmenite clusters, run the concentrate through a jig or finer pan session for count and character. If grains appear angular and chromite-rich, escalate to sample preservation for lab analysis. Even the most compelling field signs eventually hit a wall. Pans full of pyrope garnet, ilmenite streaked with chrome, magnet-positive grains, all exciting. But until a diamond is physically recovered or a lab assay confirms their presence, everything remains speculative. That's why knowing when to escalate to formal testing, and what type of test to choose, is the pivot between hobby and serious exploration. The critical threshold is indicator density and repeatability. If your grid samples consistently return 5 to 10 grains of pyrope garnet, angular and unabraded, in multiple sites across a defined area, and these are accompanied by ilmenite and chromite, it's time to take the next step, especially if you're working within known or suspected cratonic terrain. Once these conditions are met, two paths emerge: microdiamond recovery and heavy mineral mineralogy. Microdiamond recovery is the definitive assay. A bulk sample, typically 250 to 500 kilograms of weathered rock or soil, is processed via caustic fusion. This means dissolving all silicates using sodium hydroxide or similar agents, leaving behind undissolved microdiamonds and indicator minerals. Labs then sieve and examine the residue under binocular microscope, finding even a single microdiamond, usually 0.1 to 0.5 millimeters, confirms pipe fertility. This test is slow, often 4 to 8 weeks turnaround, relatively expensive, around $1,500 to $3,500 per sample, depending on volume and country, and destructive. But it's decisive. Multiple microdiamond recoveries, plotted against sample locations, can guide trenching or drilling. Their size and morphology, e.g., octahedral versus resorbed, even hint at potential macrodiamond presence. The mineral chemistry path, by contrast, tests the indicator suite itself. Using electron microprobe analysis, EMPA, or laser ablation ICP-MS, labs analyze the elemental composition of garnet, ilmenite, and chromite grains. Pyrope garnets high in chromium and low in calcium, G10 chemistry, are particularly significant. They indicate high-pressure mantle origin compatible with diamond formation. Ilmenite with specific TMG ratios and low Fe content can confirm derivation from a fertile kimberlite. This analysis is often faster and cheaper, $30, $100 per grain, with packages available for bulk grain testing, and it builds a detailed fingerprint of the potential source. However, it doesn't confirm diamonds, it merely strengthens the case. Many exploration companies use this as an intermediate step before committing to bulk caustic fusion. Another option, though less common at the early stage, is indicator mineral concentrate X-ray sorting. Some labs can scan sieved concentrates for high density, transparent crystals, and pick potential diamonds or moissanite before destructive tests. This is fast and non-destructive, but less accurate for very small stones. If field recovery includes even a single suspected diamond, however rough or small, verify its identity before sending anything to a lab. Thermal and electrical conductivity tests, SG via water displacement, 3.52 for diamond, and a loop exam for facet doubling or surface features can rule out moissanite, zircon, or quartz imposters. Field work confirms what prospectors hope. You've got fertility, perhaps even microdiamond recovery. But excitement quickly gives way to a harder question. What's it worth? The diamond market is complex, opaque, and shaped less by weight alone than by the elusive triad of color, clarity, and cut potential. And if you're sitting on rough, uncut material from a verified pipe, its value can range from negligible to life-changing, depending on what's inside and how it gets to market. Let's start with rough diamond pricing. Unlike polished stones, which are graded by the 4CS, rough diamonds are sorted into thousands of categories by size, shape, and clarity before any cutting happens. The De Beers sorting system, still widely used, splits rough into gem, near gem, and industrial classes. Gem quality rough fetches the highest prices, ranging from $100 to over $2,000 per carat, depending on transparency and crystal form. Near gem may bring $25 to $150 per carat, while industrial grade, used for abrasives, often sells for less than $10 per carat. But size and shape compound value. A 1-carat octahedral gem-quality crystal might fetch $600. A 2-carat stone of the same type can command triple or quadruple, because yield from cutting improves. A 5-carat rough of similar quality may exceed $10,000, depending on internal inclusions. Conversely, A flat or heavily included 5-carat crystal may be worth less than a clean 1.5-carat piece. Then comes origin. Pipe-derived diamonds carry prestige, especially from verified kimberlite pipes with stable production history. In Canada, stones from the Akadi and Diavik mines command premiums due to their ethical sourcing and documented chain of custody. Similarly, South African and Russian stones from historic fields are trusted by markets. If your find comes from a new or undocumented pipe, it must pass additional scrutiny. Labs may require multiple test submissions before certifying origin or issuing valuation. Rough stones must be handled with care to preserve their value. Chipping, scratching, or even high-pressure washing can damage natural surfaces used in valuation. If you suspect gem-grade rough, wrap each piece individually, avoid ultrasonic cleaning, and store in dry containers. Never apply oil or polish to enhance appearance. Labs detect such treatments immediately, and it compromises credibility. Selling rough requires a strategy. You can sell directly to licensed buyers or cutters, common in regions with established diamond markets, e.g. Antwerp, Surat, Gaborone. Work with a diamond tender house, where stones are auctioned to vetted buyers. Partner with a mining firm, granting them rights to develop the site in exchange for a percentage of extracted value. Each path has trade-offs. Direct sales yield quick cash, but risk lowballing. Auctions and partnerships may take months, but offer transparency and legal protection. Don't overlook regulatory compliance. Most countries with diamond-bearing terrain enforce strict export controls under the Kimberley Process Certification Scheme, KPCS. Selling or transporting rough diamonds without certification is illegal in member nations. Ensure your material is documented, from field recovery through lab submission. This protects not only legal status, but value too. Once real value enters the picture, so do new risks, fraud, misrepresentation, and buyer traps. And that's where the next step becomes critical. How do you protect your find and your interests from predatory offers and industry pitfalls? The moment a diamond enters the conversation, predators circle. Whether it's a rough gem in a vial, a confirmed fertile pipe, or even a promising indicator suite, opportunists, often posing as buyers, consultants, or middlemen, appear with offers that seem urgent, lucrative, and one-sided. The diamond sector has a long, documented history of underpricing, fraudulent deals, and chain of custody breakdowns. Protecting a legitimate find begins with understanding how fraud operates and how to preempt it. The most common trap is the early buyout. A speculator offers cash for your rough stones, often just enough to feel tempting, but well below market. These deals usually include pressure. The offer expires tonight, or this buyer's flying out tomorrow. The red flag? Any buyer who rushes your decision or refuses independent valuation is not acting in your interest. In known cases, 1-carat gem quality roughs have been bought for $200 and resold the next week for $5,000. Chain of custody failure is another major risk. If you allow your rough stones to be transported or handled without documentation, photos, weight, dimensions, and location, they can be swapped, diluted, or claimed as someone else's. Always document the discovery process. Photograph each specimen next to a scale and location tag. Use tamper-evident bags. Maintain a field log with GPS data, sample depth, and pan count, especially if others are present during recovery. Mislabeling fraud often occurs at the testing or brokerage stage. Some intermediaries may claim your stones failed testing, offering to buy at a discount, only to pass the same stones to another buyer as certified rough. Avoid sending samples without signed chain of custody paperwork and lab test agreements that allow you to witness or verify the results. Reputable labs like GIA, SGS, or Canadian gemological institutions issue certificates tied to unique sample IDs. In high-potential terrain, claim jumping becomes a legal weapon. If you haven't secured mineral rights or filed your find with the proper authority, someone else can stake it legally out from under you. In countries with public registry systems, e.g. Canada, Australia, file a notice of interest or stake a mineral claim the moment your sampling shows repeatable indicator results. In private land areas, negotiate access and rights clearly, with written contracts, even if just for continued sampling. When it comes to partnerships, be cautious. Mining companies may offer to fund development in exchange for access, but structure deals carefully. Retain control over data, sampling rights, and testing protocols. Consult a mining attorney or contract specialist before signing anything involving royalties, percentages, or exclusive rights. Even small decisions, like giving away location coordinates, can compromise your position. A smart safeguard is delayed disclosure. If you're sitting on strong field results but lack full control of the site, hold back key data, exact GPS points, sample depth, lab ID numbers, until legal protection is in place. This doesn't just protect you. It ensures any future buyer or partner respects your work and investment. Speculation ends where proof begins. The field may whisper promise, indicator minerals, anomalous terrain, even recovered microdiamonds. But the industry only listens when multiple, independent lines of evidence converge. This is the moment where casual interest becomes certified discovery. When tests across mineralogy, petrology, and recovery confirm that a specific site holds not just potential, but a diamondiferous source. First comes mineral chemistry correlation. Lab-verified indicator grains, especially pyrope garnet with low Chow and high Cr2O3, the so-called G10 garnets, signal high-pressure mantle derivation. When these are found repeatedly, across a grid, and co-occur with chrome diopside and magnesian ilmenite, they form what exploration geologists call a fertility signature. If these grains are angular and unabraded, they point to proximity, not just regional drift. Next is rock conformation, a physical sample of kimberlite or lamproite, properly classified by thin section petrography and whole rock geochemistry, confirms that the host lithology is correct. Look for brecciated texture, matrix-supported xenoliths, and olivine macrocrysts. Serpentinization, alteration of olivine to serpentine, typical of weathered pipes. Mineral inclusions, chromite, perovskite, and sometimes phlogopite mica embedded in matrix. Geochemistry, high MgO content, greater than 25 Wt%, elevated Ni and Cr levels, and trace elements typical of ultramafic volcanic origin. Then comes the bulk sampling phase, a true litmus test. Collect 200 to 500 kilograms of weathered rock or stream sediment from within the defined anomaly. This sample is processed via caustic fusion, dissolving silicates and isolating microdiamonds down to 0.1 millimeters. Reputable labs provide not just recovery numbers, but morphological classifications: octahedral, dodecahedral, twinned, or resorbed crystals, which give clues to how intact the eruption process was. In successful assays, even a single microdiamond proves fertility. Multiple recoveries from a compact sample area not only confirm the presence of diamonds, but also suggest sufficient concentration to justify further investment. Trenching, drilling, or bulk tonnage testing. Complementary tests tie the findings together. Magnetic survey overlays show circular low-to-mid anomalies consistent with pipe-shaped intrusions. Resistivity, or EM, scans reveal conductive halos around alteration zones, typical of serpentinized kimberlite. Soil geochemistry may show Ni, Co, Cr, and Mg spikes, especially around pipe rims. When these elements align, mineral suite, chemistry, rock type, and microdiamond recovery, the case is airtight. You're no longer speculating. You found a diamondiferous pipe. But discovery isn't the end. It's the beginning of choices. What now? Keep the find quiet and pursue development? Partner with a company? Sell samples? License the data? Each path offers different risks, timelines, and returns. Understanding your options is what shapes the future, not just of the pipe, but of your role in its story. You've confirmed it. The indicator suite checks out. The rock is real kimberlite, and microdiamonds, perhaps even macros, have been recovered from your grid. This isn't theory anymore. The data tells a consistent, verifiable story of a diamond-bearing pipe. But now comes the strategic crossroad. What to do with the discovery, and how to choose between control, collaboration, or capitalizing through transfer. The most direct option is staking and keeping the claim. In jurisdictions that allow private mineral claims, such as Canada, Australia, parts of the US, and select African nations, you can formally register your discovery, securing rights to explore and potentially develop the site. This grants you time to conduct deeper sampling, seek partners, or apply for a prospecting license. But holding a claim isn't passive. In many regions, you must perform annual work, trenching, sampling, or surveys, or pay fees to maintain your rights. Letting them lapse exposes you to poaching, sometimes within days. If you choose to develop the find independently, you'll eventually need to scale from hand tools to mechanized trenching or even core drilling. That requires capital and technical support. For this, you might seek a joint venture with an exploration company. In these deals, you retain a percentage interest, commonly 10 to 25%, while the partner funds further exploration and development. Key here is negotiating strong terms. Retain input on testing protocols, maintain data access, and define exit clauses if milestones aren't met. Another path is licensing your data. If you've documented indicator results, grid locations, recovery stats, and GPS tag photos, that package itself can be sold or licensed to a larger entity. This is common among advanced prospectors who prefer to hunt, not mine. In exchange for your data and rock access, you might receive an upfront payment, a success-based royalty, or a retained override if the site progresses to mining. A few choose to sell rough stones directly, particularly if macrodiamonds were recovered. This demands extreme care. Every rough diamond must be certified under the Kimberley process to be exported legally. Find a recognized gem lab, GIA, EGL, or local equivalents, and request full reports on carat weight, clarity, color, and crystal morphology. Once certified, the stones can be auctioned, consigned to cutting centers, or sold at tender houses. But remember, once the stone is sold, so is your leverage. The data attached to that rough may be what tips someone else to stake around you. Some prospectors go another route: silence and stealth. They delay filing claims, continue collecting data, and slowly build a stronger case before announcing the find. This approach requires trust, discretion, and often more legal shielding. But when done right, it lets you approach major partners from a position of strength, with both the rock and the paperwork in hand. No matter the path, the essentials are the same. Document everything, consult a mineral rights attorney, and treat every decision from here as a business move. You've crossed from exploration into asset management. A verified diamond pipe is more than a geological event. It's a socio-economic ignition point. Whether it sits beneath a ridge on private land, a forgotten basin on tribal territory, or a government-controlled concession, the ripple effects begin the moment the find becomes known. Community expectations rise. Land values shift. Local labor demand stirs. And far beyond the field, traders, cutters, and even regulators start watching for a new source to enter the stream. Local impact comes first. In rural or underdeveloped regions, news of a diamond-bearing pipe, even unmined, can alter property dynamics overnight. Landowners may suddenly face interest from speculators, leasing offers, or even illegal diggers. In some areas, artisanal miners move in before legality catches up, operating informally and often dangerously. The discoverer, especially if they hold the claim, must decide how to balance protection with participation. Some choose to partner with a local community, hiring residents for early-stage work, trenching, sampling, guarding the site. This builds goodwill and deters illegal activity. Others work with local cooperatives or tribal councils to establish joint use rights. These arrangements are delicate but powerful. When structured well, they protect access while preventing conflict. When neglected, they can turn promising discoveries into litigation and loss. In established mining nations, a new pipe can shift the market landscape. Traders begin speculating on future supply. Cutting centers, especially in Antwerp, Surat, and Gaborone, inquire about origin and type. If your stones exhibit unique morphology, unusually clear octahedrons, rare color saturations, or consistent fluorescence, they may carve out a niche identity. Think Canadian ice diamonds, or the yellow stones of Ellendale. A single find, well managed, can put a locality on the map for decades. This extends into certification and branding. Governments may promote finds as part of ethical sourcing campaigns. Labs may issue origin-specific reports if sufficient documentation and sample submission protocols are followed. In some cases, entire mining ventures have been built not just on stone value, but on the verifiable story behind their recovery. But discovery also carries environmental responsibility. Kimberlite pipes are often found in fragile ecosystems, wetlands, highland meadows, or forested craton zones. Sampling alone can disturb local hydrology. Bulk testing, if unchecked, may lead to sediment runoff or soil destabilization. Regulatory authorities often impose impact assessments before approving any further development. Forward-looking prospectors preempt this. They keep disturbance minimal, restore trench sites after testing, and maintain logs of material moved. These records matter, not just for permitting, but for future partnerships. Any mining company considering your site will assess your footprint. Clean records translate to faster approvals and smoother transitions from prospecting to development. And what about the broader legacy? For many, the true value of a discovery isn't just monetary, it's generational. That GPS point, that pan full of red garnet and heavy black grains, might reshape a local economy, birth new careers, or open forgotten geology to fresh eyes. But before that can happen, there's one last step: distilling the full journey. Lessons learned, mistakes avoided, and signals every future explorer should watch for.